Good morning. We'll continue discussing the various perturbations that we have on the hydrogen atom. Last time we sort of started discussing the spin-orbit interaction. Remember, we had these two terms. Okay, let me put this stuff on the board because we'll need it again. Again, we have the electron around the proton with some angular momentum, and we discussed what the interaction between them would be. Okay, so the spin-orbit interaction is the magnetic field felt by the electron due to the proton and the magnetic moment, that's the magnetic moment of the electron. So the magnetic field was, okay, if you take some radius r, mu 0 over 4 pi, E times V divided by R squared. Okay, so that's B due to the proton. And we put in certain factors here. Okay, we put in an M and R so that this could be written as an angular momentum. Okay, obviously I have to divide and multiply by it. And also we divided and multiplied by epsilon 0 so that we are going to get, okay, that this MVR is just going to be the angular momentum of the electron because we are putting the electron mass, okay, angular momentum of the electron, and then we have factors which go like mu 0. Well, mu 0 disappears because mu 0 epsilon 0 is 1 over c squared. So 1 over 4 pi epsilon 0. I have a charge, E, in the numerator. And then I also have a 1 over mc squared, right? Mu 0 epsilon 0 is c squared. So mc squared and a 1 over r cubed. Okay, so that's the magnetic field. So, and also if you look at the magnetic moment, we just went through a similar analysis. If you have the electron moving around with some velocity, okay, the magnetic moment of the electron is something like, okay, current times the area, which is going to give me E over, okay, 2 pi r over v times pi r squared. Okay, so this is going to give me, again, canceling some terms here, E times r times v over 2. So if I multiply and divide by m, again I get the angular momentum, but this time I am interested in the spin of the object. So this sort of says that what you get here, the type of angular momentum that you get here, is independent of the radius, how the charge is distributed and such things. So I can just put in the spin angular momentum here. So it's going to be E over 2m times the spin. Okay, so, but there is this correction factor, okay, the gyromagnetic factor. Okay, so this is 2.000 something, which effectively, okay, cancels that too. Okay, not exactly, but effectively. Okay, so we end up with an equation which says that mu E is going to be equal to minus, because the charge is negative, E over m times s. Okay, so our H spin orbit becomes something like, just combining these terms here, E squared over 4 pi epsilon 0, okay, m squared c squared 1 over r cubed, and then I have okay, I forgot the L here. Okay, L dot S. Okay, so that's where we were last time. All right, so we now want to find out what the first order change in the energy is going to be. And we want to find a, okay, so E spin orbit first order is going to be the expectation value or diagonal matrix element of this HSO between the eigenstates. Okay, so I have these NLM, okay, HSO, NLM, but you see there's also the spin wave function, so I have to include the spin as well. So 1/2 ms, and I have to do the same thing over here. So let me just move that out to the left. ESO first order is going to be 1/2 ms. Okay, so this is going to be the first order energy, but the problem is that this L dot S term, okay, so I'll need two types of averages. One average will be over space, over the radial coordinate. I have to find what 1 over r cubed is, but I also have to find the average value of L dot S with respect to the angular momentum and spin coordinates. Now, whenever you have something like this, dot product of two angular momenta, the okay, your reflex would be to look at the sum of these things. Okay, so if you look at L plus S, okay, which was our total angular momentum, okay, for these two objects, if you look at the square of this, this is going to be L squared plus S squared, okay, plus 2L dot S. Remember that L and S are in different Hilbert spaces, so okay, they commute. So I'm going to get this L dot S is equal to J squared plus minus L squared minus S squared 1/2. Now, the nice thing about this is that you see L dot S, if I now look at the eigenfunctions of total angular momentum, okay, so the total angular momentum, objects had the total angular momentum index J and the Z component Mj, okay, J and Mj. Okay, usually we also include L and S here to specify how this was constructed. Okay, it was constructed from angular momentum L and S. Okay, but these are the main indices. This object is an eigenstate of not only J squared, but it's also L squared and S squared. Okay, so I'm going to, if I, instead of these outer product states that I have here, okay, Lm 1/2 ms, if I use the total angular momentum states, then, okay, everything is nice and diagonal and I know the eigenvalues. So what I do is, instead of writing it this way in terms of the L and M and ms, what I'm going to do is, okay, so if you like, I'll move this to the left one more time. So this would be sum result of spin-orbit coupling based on L, well, actually everything, right? N and L and M and MS, okay? Instead, what we can do is we can look at the spin-orbit coupling as a function of N and J and MJ, okay? So in terms of those variables, when I go to the total angular momentum space, then I'm going to get, okay, just these J, MJ, okay, H, S, O, J, MJ. Okay, this is a little misleading because I still have the and L pieces, the radial average is still there. Okay, so these are the radial parts and these are the angular parts. Okay, so what do I get out of this? So I'm going to get, let me just perhaps explicitly write it out. So I have E over 4 pi epsilon 0 m squared c squared, okay, expectation value of 1 over r cubed, okay, that's the radial average with respect to the n and l variables, okay, and then the expectation value of the, where am I, L dot S with respect to the J, MJ coordinates. Okay, but I know that these things are L dot S. These eigenfunctions are eigenfunctions of L dot S. So I'm going to get, let me just squeeze the angular part result over here. E squared, right? E squared 4 pi epsilon 0 m squared c squared average of 1 over r cubed, okay, and L, which I still have to figure out. But this thing here is just 1/2, okay, J plus 1 minus L plus 1, and spin is always 1/2, it's always 1/2, so it's going to be minus 1/2 3/2, okay, h bar squared. Okay, so all I need is this 1 over r cubed average, which can be obtained through a recursion relation, okay, which I am not going to discuss here. It's not difficult, but quite tedious algebra. But I'll just write down what the result is, if I can read it. Okay, so 1 over r cubed averaged over the hydrogen wave functions is going to be equal to 1 over L plus 1/2, okay, L plus 1 a cubed. Okay, so there's a Kramer's recursion which relates, for example, 1 over r cubed average to 1 over r squared to 1 over r. Okay, so let me just at least, okay, between things like 1 over r to the s, r to the s minus 1, r to the s minus 2. Okay, so for example, we know what the average of 1 over r is, that comes from the potential. We know the average of 1 over r squared, which we obtained from the Hellman-Feynman equation. And this relation allows you to go one power down, so that you can, using this relation, you can go up and down in powers in R, which is very convenient, but not very transparent, really. Okay, so that's that. So let's just write this in its full glory one last time. So E spin orbit, first order, is going to be equal to E squared over, there's a factor 1 over 2, so 8 pi epsilon 0, m squared c squared, okay? And then I have the h bar squared and a fraction which involves this denominator, L plus a half, L plus 1, a cubed, and the numerator has j plus 1 minus L plus 1 and minus 3 over 4. Okay, so this is the spin orbit, the shift in the energy to first order due to this spin orbit coupling. Now, this, you see there's this term m1 over mc squared here and something like the energy in the numerator. So this also turns out to be the same order as the H relativistic that we found out earlier, right? So E relativistic that we found out, the first order, was what? Okay. Minus En squared, let me see, or 2mc squared, and then I had 4n or L plus a half minus 3. Okay, so these are two objects to same order. Okay, the prefactors, this is the Bohr radius, so you have to expand that and see what that is, etc. So it brings out something which is again proportional to this thing here. So what we do is we add these things up, okay, and the sum we call the fine splitting effect. So the H fine splitting is the relativistic correction, okay, plus H spin orbit. Okay, so their sum, they together make the fine structure correction to the energy levels. So the E fine structure to first order is going to be E spin orbit first order plus E relativistic first order. So I'm going to add them up. So you might decide that it's going to be something extremely complicated. But what magically happens is that the sum gives you En squared, okay, divided by 2mc squared. Okay, that part isn't surprising because you want things to be to that order. But now we get, 3 minus 4n divided by j plus 1/2. Okay, so it looks unbelievable. Okay, the first time I saw this, I didn't believe it. So there's a problem in your textbook which you can solve. It's amazing that you add these things term by term, and you do get exactly that. Okay, so it's a nice simple expression which tells you the splitting in the energy due to these effects, okay, to first order. Okay, so I'll not do the algebra. The algebra is straightforward, but not very exciting. Okay, so that's what we have for fine structure. Now, what we are going to do next is to look at the hyperfine structure effect. So if I want to do that, let me just do it on this side of the board. So the hyperfine, okay, correction to the hydrogen atom comes from the, yes?
Are same order corrections always separable like this?
What do you mean separable?
To some, I don't know, when we had p squared in the relativistic case, for example. In this case, we had 1 over r cubed. They might have been the same. So what I'm asking is, are same order corrections always separable in some way?
No, actually, this is, I can't really give you that much of an intuition why these things should, okay, give things to same order, because remember, this H relativistic was something related to V squared, so it came in with a factor 1 over R squared, right? Whereas here we have 1 over R cubed. So things are a little different. Still, the order of the term turns out to be the same, and when you add them up, you get this. Okay, so these are two different separate effects. Okay, which we just add up and find this.
I'm asking why summing is legit. It doesn't have to be the case, I guess, because the wave functions change with the first correction you make, and then you make another correction of the same order. Mm-hmm. So this sum. Okay,
okay. Let's look at that. We have some H0. Okay, and then suppose I have a number of further effects. In fact, we are going to see a nice example of this when we start discussing the magnetic field. So suppose I have something which I am going to include, okay, so let me call them A so that there's less confusion. I have two effects which come in like this, okay? So ordinarily what I would need to do is I would need to look at when I look at the total, say AB, first order energy, I would need to look at N, okay, the zeroth order, what did we call it, psi N0, okay, HA1 plus HA1, okay, psi N0, right? That's what I would need to do. So it would just give me the correction due to this and the correction due to that. What we are doing here is a little, okay, more than that, because here when we are using these H and zeros, we have a choice in terms of the spin wave functions. We can use the spin wave functions in the outer product, okay, form, or total angular momentum form. Okay, so it turns out that for the spin orbit coupling, it is better to use them in the total angular momentum form. For the relativistic one, it doesn't matter. Okay, for the relativistic one. So we turn out, we say, okay, we are going to use the same sort of things over here. But when we come to the magnetic field, we are going to see that depending on the strength of the magnetic field, we may want to use one form or the other form, okay? Or, okay, something in between when we do that. But basically, to first order, you can just add these things up, okay? Other questions? All right. So let's look at now yet another one, Hc. Okay, so this time I'll call it H hyperfine. That's going to be minus the magnetic field produced by the magnetic moment of the proton. Okay, so that was because I was going around in an orbit, okay, around the proton. This time I'm going to look at the magnetic field due to, how do I say this? Let me call it mu proton. That is going to be due to the magnetic field produced by the proton dot, okay, the magnetic moment of the electron. Okay, so this time what we are looking at is I have this proton here, which is generating, okay, it's mu proton. It has a magnetic moment. It generates a magnetic field, which goes around like this. Okay, and then the electron is somewhere over here. Okay, so it has also its own magnetic moment. Okay, so the energy due to the presence of the magnetic field due to the proton magnetic moment dot mu e. Okay, so we have to figure these things out one by one. The magnetic moment of the proton is something which is very similar to what we have here. Okay, the proton has the charge, positive charge, and then you have this factor E over 2m, okay, times the times the spin of the proton, okay. So angular momentum of the proton, which is the spin of the proton. So it's exactly the same thing as the electron case, except that in the electron case, we multiply that with some GE. Now we have to multiply this with GP, which is the relativistic correction. Okay, relativistic correction. And GP is something actually quite larger, around 6. See if I have it here. Yeah, 5.59. Okay, so proton is a more complicated object. Okay, it's not, it's made up of quarks and things, so you need a better correction. In fact, that's an experimental value. Okay. So that's the magnetic, that's the proton magnetic moment. Now, the magnetic moment due to this mu proton is going to be what? We are now experts in this in electromagnetism, right? You have this mu 0 over 4 pi factor, right? And then it goes like 1 over r cubed. And I have 3 times mu dot r times r minus mu, right? So that's the magnetic field. So if mu and r are in the same direction, then this term dominates and magnetic field is in the same direction as mu. If mu and r are perpendicular to one another, then you are somewhere over here. Magnetic field is in opposite direction to the direction of the magnetic moment. Okay, so what does the Hamiltonian look like? So I'm going to get H hyperfine is equal to, okay, this thing times mu E, which I have over here. Perhaps I should write it over here again. So mu E is, remember, minus E over M times S electron. So this is going to give me this object, mu 0 over 4 pi, 1 over r cubed. There's a mu in each one of these terms, so that's going to bring me an E GP over 2m. One important point, this is now the proton mass, right? Because this is the proton angular momentum. So at this step, when I multiply both the numerator and denominator with the mass of the object, I am, in this case, I am multiplying by the mass of the proton. That's important because mass of the proton is, okay, 3 orders of magnitude higher than that of the electron. So this is going to be a much lower, okay, contribution. That's why it's hyperfine. Okay, so that's that term, GP, we put that in, and then we have to put the same thing for the electron because I now have an E over M that comes from the electron part, and then I have S proton dot S electron. Okay. Now, you see, if you were, okay, so if you remember from electromagnetism, there's an additional term for the magnetic field due to a dipole. You remember what it was? Okay. Yes, there's a delta function piece which adds to this. Okay, so there's this mu 0 over 4 pi, but there's this additional term which has some coefficient. Let me just check what that was. Let's see, 2 mu 0 over 3. Okay, so 2 mu 0 over 3 times mu times delta r. Okay, so there's a delta function field at the position of the proton. Okay, so why is that? You have this loop which we consider as going to a limit of a point dipole. So it has a current and some area A. So the magnetic moment is I times A. So we take the limit in such a way that, okay, I goes to infinity, A goes to 0. So, but their product is equal to mu. But if you look at the field inside, so this field that you calculate is the field outside, but the field inside, I have a very strong field, and when the object collapses into a point dipole, then I'm going to get a delta function magnetic field exactly at the origin, okay, at the position of the dipole. So in this problem, it turns out to be important. So I have to put that in, okay, and then why did I write this? Maybe I should write one more step in between. Okay, so this was the mu part. Oops. Okay, so 3, we factored out the constant in front, so it's going to be L, not L, SP, is proton dot R, okay, times R minus S proton. Okay, so I have just replaced mu with E over 2 MP, okay, whatever, like this. And then I have an additional term, which is going to be 1 over r cubed e over m. Okay, so it's in fact going to be in here, right? But mu 0 is in, so I'm a little confused. So mu 0 we can take out, plus 2 over 3 sp. Okay, so all of this thing is now the magnetic field dot the delta function is important, dot SE. All right, so what I did is I just rewrote this line, okay, replacing mu with SP times, okay, E over 2MP. All right, now if you form the inner product, you'll see that it's symmetric in SP and SE. So let me write that. Mu 0 over 4 pi. And then I have E squared GP over 2 M proton, M electron times 1 over r cubed. And what I have here is 3 sp dot r multiplied by se dot r, okay, minus sp dot se, and then I have plus 2 over 3 sp dot se multiplying delta r. Okay? So we have there a term which contains the spin operators for the proton and the electron. All right, so what are we going to do? We are going to somehow sum this over, okay, all possible angles, etc. So we have to do some sort of, first of all, radial averaging, right? So let's see what we can do in terms of the radial averaging. Okay, so E hyperfine to first order is going to be equal to, I am going to again have spin functions, okay, so I'm going to have 1/2 ms. Not only that, but now I also have the proton, right? So I also need 1/2 m proton, so this is the proton spin wave function. And I also have the positional averaging, okay, energy quantum number, angular momentum, and so on. Then I have this H hyperfine, okay, and just, okay, other stuff, 1/2 and proton, 1/2 ms. Okay, so that will be the energy states. Now again, just looking at our expression, I have things which look like sp.se. So that means it will be perhaps more advantageous at the end to look at the total angular momentum state of the proton plus electron so that I can use those eigenfunctions. Now, I have to do a space averaging also. And if I do the space averaging, I have to do it not only over this R, but also over these unit vectors R, okay? So things are, okay, going to get complicated. So what we can do is we can limit ourselves, okay, to the L equal to 0 state so that the angular averaging is going to be easier, okay? So just consider the L equal to 0 state. Okay, so if that happens, then the angular averaging is much easier. Okay, because now I'm going to look at the angular average. Okay, so the angular averaging is going to be my H here, okay, H hyperfine, and I am going to get Y 0 0 star Y 0 0 because I'm looking at the L equal to 0 state. So this is, remember, the L, and if L is 0, M has to be equal to 0. And then I'm going to integrate this over all angles and do something like this. Okay, but Y0 0 was very simple. You remember what it is? Yes, 1 over 4 pi. So the square is 1 over 4 pi. So it's 1 over 4 pi times the integral of all of this over angles. Now, this 1 over r cubed, of course, is not influenced by that angular averaging because there's no integral over r when I'm averaging over angles. But I do have to, okay, average this object over the angles because unit vector r is going to be pointing in a certain direction. Okay, so what I'm going to do is I'm going to look at the average of some quantity, okay? In fact, I'm going to look at just that first part. I don't want to write S all of the time, so what I'll do is I'll look at, okay, so there's some constant A dot R times B dot R, right? Three of them minus A dot R, A dot B. Okay, so A is SP and B is SE. So I'm just looking at that first part. I want to find the angular average of this. So, okay, this is nice and isotropic. It's unit vector in all directions. So what I'm going to do is I'm going to choose this z-axis as the direction of A. Okay, that's without any loss of generality. B is some other vector. Okay, and R is a unit vector pointing someplace. And I want to average this over all possible values of R. So R has this angle theta here. And then if I look at the X and Y coordinates, okay, that is phi. All right. So let's do this average. Okay, so I'm going to get 1 over 4 pi, an integral, or sine, or theta and phi. So I'll look at this angular part. So it's just 3 A dot R. A dot R is going to give me just cosine theta, right? So R is equal to Z cosine theta plus X sine theta cosine phi plus Y sine theta sine phi, right? So the first term here, 3 A dot R, gives me 3 times, okay, the Z component of this, which is cosine theta. Okay, times B dot R. Now B is some general vector, so it will bring in everything. Okay, so it's going to be BZ times cosine theta plus BX times sine theta cosine phi plus BY times sine theta sine phi. Okay, let me just do this part. This part, of course, doesn't contain any r, so it's just a dot b. Okay, so the average of a dot b is a dot b. Okay, there's no r factor in that. So sine theta, d theta, d phi. Excuse me. Okay, so the d phi integral gives me, okay, careful. I was going to say 2 pi, but there are terms here. So cosine phi, when I integrate over 2 pi, what do I get? 0. Okay, so this term goes away. Sine theta, similarly, so those two terms go away. And I am left with this piece here. Okay, so over here, for this term, the phi integral gives me a factor 2 pi. Okay, so I am left with 1 over 2, canceling the 2 pi's, times 3, integral cosine, 1 cosine, 2 cosine, cosine squared theta, sine theta, d theta. Okay, and now I convert this, use my standard transformation and write this as 3 over 2 minus 1 to 1 x squared dx, which is equal to what? X cubed over 3. Okay, so 2 over 3, right? So it turns out to be 2 over 3, which means that this integral averages to 1. Okay, so that means I skipped various pieces, which I shouldn't. Okay, so let's see. Here I need a factor a, right? First term, a dot r is going to be a times cosine theta, and b, so this is going to, I have an a times bz here, which I shouldn't forget. So this is a times bz. But now going back to my figure, a times bz is nothing but a dot b. Okay, so this whole thing averages to a dot b. But I have another a dot b there, which is just a constant. So I'm going to just get 0 out of this. Okay, so the result of all this calculation is that this thing just averages to 0. So the only contribution comes from this, okay, term at the very end. So now I have to look at the average of that, okay, and that's a radial average. Yes. Thank you. So I need to have 4 pi over here. Okay, and mu 0 is that. All right. So what do we have? We are going to need to find the average of this. So let's do that. Okay, I'll keep this piece on the board. So finally, if I now look at the expectation value of H hyperfine, what do I get? I get mu 0 E squared GP. Okay, that divided by 2 MPM. And then average of really this factor 2 over 3, okay, SP dot SE over the angular variables associated with the spin. Okay, so we have to look at the spin average of that, and then the radial average of the delta function. So I'm going to get here n 0, 0, because remember I am looking at the L equal to 0, 0 states, delta of R n 0, 0. Okay, because we decided that we would limit ourselves to L equal to 0 states. So this thing is just magnitude squared of psi n 0, okay, wave function at 0, at the position of the proton. So we end up with this interesting result that the hyperfine object, the interaction between these two spins, okay, is related to the value of the electron wave function at the position of the proton. Okay, so that seems to be the only place where we get a contribution from this. At all other points, the average just cancels out one another. Okay, so we get 0. It averages to 0. The only place that we get a contribution is this term that we usually ignore. Okay, so when we look at that last term in the expression for the magnetic field due to a dipole, we say, well, we are outside the dipole, so there is this mathematical curiosity at the position of the dipole, which, okay, is there, but not usually, it doesn't usually come into any play. But in this case, you see, that's the only place where the two spins actually interact to produce some amount of energy. Okay, so this thing has some value. So let me just tell you what that is. That's 1 over 3a cubed, I guess, for proper normalization. Yes, pi a cubed. Okay, a is the Bohr radius. So we are almost there. So this is going to be equal to mu 0, 2's cancel, e squared g proton, which is something like 6, divided by 3 times 1 over pi a cubed. And then I have this sp.se. Now sp.se, again, if I just want to find its eigenfunctions, what I do is I look at the total angular momentum of sp plus se. Okay, so whenever you get a dot product like this, that's what you should do. Okay, so this is the total spin angular momentum, total spin of the proton and the electron together. That's going to be sp squared plus se squared minus 2 sp dot se. Okay? And that is equal to the total, let me call it big S squared. So sp dot se is going to be equal to 1/2 big S squared minus S proton squared minus S E squared.
Isn't it plus SE? Plus SE squared.
2, oh, okay, I'm sorry. No, it's plus, oh, this is plus, okay, sorry. Okay, so that's the total spin angular momentum. So now if I want the expectation values of this thing, the sp.se term, which I'm going to write here, is going to have average of h bar squared over 2. S squared is going to have value, okay, either 0 or 1, because it's the sum, the total angular momentum of two spins. It is either 0 or 1, right, minus, okay, these things are the same. It's going to be 3 over 4 and 3 over 4. And that's it. So the upper sign is when I have opposite spins, okay? So that corresponds to the total angular momentum equal to 0 case, which is the singlet case. So let me just squeeze here some notation. So this is singlet, and the lower one is the triplet state. All right, so the end result of all of this, I'm anxious to squeeze everything here, mu 0 E squared GP divided by 3 pi A cube. There's an H bar squared. And I'm going to get either a minus 6 over 4 for the singlet state, or, okay, 1 minus, so that's minus 2 over 4, right? Please check my algebra, for the triplet state. So depending on whether the proton and the electron spin are in the same direction or not, you get this very, very, very slight energy change. This is of the order of micro electron volts. Okay, so the difference here between these two energy levels is of the order of, I think, 0.5 or 0.6 micro electron volts. So that's a very small amount of energy, but it's also quite sharp. Okay, you have these two distinct energy levels, and there will be transitions between them. So if you look at the frequency associated with this, so if you look at what h bar omega is, well, h bar, let's call it 2 pi f. Okay, so the frequency is 1.2 something, I think 1.4. Do I have it in my notes? Yeah, 1.4, in fact, it's like 1420 megahertz. So it's 1.4 gigahertz, which is in the microwave region. And it has a wavelength of 21 centimeters. So this is the famous 21 centimeter line. So if you turn your radio telescope to any point in the sky, of course you have the background radiation, but there's also a very nice sharp line at this frequency that's called the hydrogen line, and it's very significant, it's very distinct when you look at the spectrum. Okay, so let's give our break and we'll continue.